So here's like the next big thing, and this is the last of the really big topics. By the way, are we recording today?
Mm-hmm.
Okay. So your third quiz before the big test is tomorrow. Okay. And that's going to kind of be like the big culminating thing. You have to do titrations like in stages, like, hey, here's just, say acetic acid. Then we're going to add like 10 milliliters of hydroxide to it. Add another 10 milliliters and go in stages. Y'all did 2 worksheets on this, okay? Here's going to be the most critical parts is when you reach the point where if it's half neutralized, what's the relationship between pH and pKa?
They're the same.
They're the same, only when it's half neutralized, okay? So on like a pH volume curve, okay, you got some action like this going. So here's your equivalence point. Here's your half the equivalence point. At that point, your pH equals your pKa. So remember, prior to this point, the dominant species is the acid, because of the fact that what's happening is your acid is reacting with that hydroxide to form the anion and water. So you're starting off with all the acid. As the reaction goes, this concentration is decreasing because it's being used up, but you're producing anions. Okay, so this is kind of like what Brent asked about yesterday. Hey, this is kind of turning into a buffered solution. So prior to that equivalence point, you have a higher concentration of acid than you do at anion. At half the equivalence point, these two concentrations are equal, and that's why when you look at that Henderson-Hasselbalch equation, pH is going to equal pKa, because of your anion divided by the concentration of the acid. Well, at half the equivalence point, these two concentrations are the same. You're taking the log of 1, that's 0, it drops out, the pH equals your pKa. After you get past that point, then your anion concentrations become bigger. Then you're taking the log of a value bigger than 1, and your pKa, or your pH, then becomes greater than your pKa. Now, at the equivalence point, and I promise you, you're going to have to do one like this. When you reach that equivalence point, and you have completely neutralized this side of the equation, this is when you're going to have to do that secondary reaction, okay? You're going to take the anions, so that secondary reaction is going to be that anion reacting with the water to form the acid and hydroxides. So remember, on your rice chart, and this is huge, this actually has to be in molarity. So you got to take the number of millimoles that you have divided by the total volume to get that molarity. 0, 0. Now, so that's one thing that you have to do. Take the number of millimoles divided by the total volume to get the actual molarity. Y'all have done this, okay? But since this is acting as a base, what are you going to have to do with the Ka value?
Find the KB.
Yeah, so you got to find the Kb value. Then when you find X, what are you finding?
The hydroxide.
The hydroxide ion concentration, okay? And then you take the negative log of that, you get your PO8, subtract from 14, okay? So if you're not sure and you're not solid on that, go back. You did 2 assignments, okay, where you're doing this in stages. So make sure that you've got that down. Now, I'm not going to make you like write down the names and formulas of strong acids. This is a little bit different twist. So what I'm going to do is I'm going to give you a list of chemicals, and you're going to tell me, hey, is this a strong acid? Is this a strong base? Is this a weak acid? Is this a weak base? Okay? So pretty much, if you know your strong acids, guess what? Hey, if it's not one of those, it's going to be a weak acid. All the strong, and if you're not sure about your strong bases, look at that one of those on that very first day. I gave you so the journey begins. This list of all is 1 page front to back. Okay, go look at all your strong bases. What do all the strong bases have in common?
Hydroxides.
Hydroxides. Okay, all right. So there you go. So you might look over like those Kb values. Go in the back of the book. Hey, what do all my Kb values have in common? Oh, they all have a lot of hydrogens that can give up, okay, and that's the whole point, okay? All right? Okay, we're good? Fantastic, going once, going twice. So that's this, and this quiz, unlike the other ones, will be like a front to back kind of thing, okay? Just because I'm going to give you space to do all those calculations. All right. So, with that said, so let's chit chat about Ksp and Qsp. So it's the same idea in terms of how this deal is going to play out. So what's going to happen is this. So I've got, to show you, I've got some 1 molar magnesium nitrate and I've got some 1 molar sodium hydroxide. Now, to really understand what's going to happen here, is that you have to understand more so than any other thing we're going to do, kind of what's happening on an atomic level. So what I'm going to do is I'm going to mix up, let's say, 2 milliliters of a 1 molar solution of magnesium nitrate. And then I'm going to add to that 2 milliliters of a 1 molar solution of sodium hydroxide. Okay? Now, this is also where it's handy to know your solubility rules. Magnesium nitrate, soluble or insoluble?
Soluble.
Why?
Nitrate's always
All
soluble.
nitrates are soluble. Then you have sodium hydroxide. All group 1s are soluble. Okay? So that's soluble. So here's what's important, is that within these solutions that I'm going to mix up, okay, and this is what you have to visualize. I've got magnesium ions floating around, and I have hydroxide ions floating around. And over here I have sodium ions floating around, and I have hydroxide ions floating around. Okay? It's most important, right? So when I mix these together, okay, so I'm going to take some magnesium nitrate and I'm going to take some sodium hydroxide. And so these are going to get mixed together. So when I mix those together, okay, when I mix those together, in this sea of chemistry, so to speak, I've got magnesium ions chilling out, I've got some hydroxide ions floating around, I've got some sodium ions, I've got some some nitrates. These are nitrates. Hold on. Let me back up the bus.
Yeah, they're hydroxide up above as well.
Nitrates. Okay? So that's nitrates. Now, also within this, what else is there that I haven't drawn? There's a lot of.
Water.
Water, okay? There's a bunch of water molecules that are lurking within this too. Now, what makes something soluble is basically the magnesium ion bond. If you look at a water molecule, you got the dome of negativity up here on the oxygen end, and the hydrogen end is positive. So when I mixed up that solution of magnesium nitrate is a white powder. I dumped that in with the water. It dissolved because the attraction for the magnesium ion for the water molecule is stronger than the attraction is for the nitrate. If the nitrate bond was stronger, it would stay as magnesium nitrate and it wouldn't dissolve. Same thing is true of the sodium hydroxide. Okay, when we mix up sodium hydroxide, it's a white pellet. Okay, potassium is more bound to the water than it is to the hydroxide. Hey, it dissolves. So this is a tug of war between these cations and these anions and these water molecules. So depending upon which one wins, that determines whether or not it's soluble or insoluble. So within this ocean of ions, we got a whole bunch of water molecules that are trying to pull because they're positively and negatively charged. We got magnesium being attracted to the hydroxide, we got sodium attracted to the hydroxide, we got nitrates attracted to everything else because they're oppositely charged. So we have a whole bunch of interactions going on right now, okay? they're attracted to the water molecules, but then they're also repulsed because the magnesium and sodium, they don't want to be near each other because they're positively charged. The nitrates and hydroxides, they don't want to be near each other because they're negatively charged. So you got repulsion and attraction. It's like, you know, this soap opera happening in this beach. It's like, who's attracted to who? Who's going to hook up? Ooh, okay. That's basically it's romance on a chemical level. All right.
So that's where they say there's chemistry between
There it is.
people.
That's it. Okay, so let's take some sodium hydroxide, right? Doink, doink, doink. Now this is horribly imprecise.
Slow.
That's about 2 milliliters, give or take. So then I'm going to take my magnesium nitrate.
Give or take.
Okay, also a clear solution.
Precipitate.
Not for long.
And when I do this, I get this white, and I love this word, gelatinous precipitate. Okay? Gelatinous, it's a good word. Okay? So, it looks like curdled milk, one of the two. So, here's the point, is that something went from being ions floating around in a clear solution to now they've hooked up and now they're a couple. Okay? So, our task is to figure out who hooked up. Okay? That's the $1 million question. So it's like clue, right? So could the nitrate and the hydroxide have hooked up?
No.
No.
Why not?
They're both negative. They don't want to be that way.
Same thing with the magnesium and the sodium.
Right.
Not cool. Same charge. Now, the magnesium could try and hook back up with the nitrate, right?
Good.
But if that happened, the magnesium nitrate would never be soluble in the first place, right? The sodium could try and hook up with the nitrate,
No.
but that's not going to form a precipitate. Why?
Because sodium
Sodium, they dissolve in the first one.
Yeah, they're both soluble in the first place. So group 1s are all soluble. Nitrates are all soluble. Okay? So that's not going to happen. So what does that leave us with?
Magnesium
and
hydroxide.
Okay?
Two
Now-
hydroxide.
Here's the dichotomy that exists. So when you're talking about, if you were in Chem 1, or even Chem 2, and I said, hey, let's write the net ionic equation for what's happening, okay? Here's what you all would do. You would write, okay, I got magnesium nitrate, so we'll do the Chem 1 version of this. And then we get magnesium hydroxide and NaNO3. Okay? We'll balance it. We'll throw a 2 over here. Okay, now we got 2 sodiums. Then we got 2 sodiums, we got 2 nitrates. Everything's cool, we're balanced. Okay? So there's the Chem 1 version of this. Oh, it's a double displacement reaction. Okay? Maybe Mr. Sturts had you all draw the posters with the cartoon things with the different types of reactions. Okay? You can visualize this as being like at a dance, okay? You got prom coming up, okay? So here's one couple, here's another couple. Halfway through the song, they switch partners,
I think
okay?
it's NO3 too.
Huh?
I think it's NO3 too.
Yeah, the first one.
Yeah, you
What?
just did NO
NO3.
at the beginning of the equation.
Oh, my bad. NO3 too, there we go. You don't do what I meant, okay? There we go. So, and this is the Chem 1 version of this. It's a double displacement reaction that's balanced, cool. Now, but if you're going to look at the net ionic equation, which is kind of the nuts and bolts of this, what's happening is that you have magnesium, because the nitrates are soluble, your sodium, they're soluble, so those are going to be your spectator ions. So you had Mg2 plus 2 hydroxides yields MgOH2, okay? So, in terms of forming the precipitate, this is the reaction that took place, okay? Now, when you look at how you're going to calculate Ksp, it's products over reactants, right? Even though this is what's forming the precipitate, this isn't what we're going to focus on. What we actually need to focus on is if you had a bunch of magnesium hydroxide, and this is the paradigm shift that you have to make. when you look at how that Ksp is calculated, it isn't based upon the formation of a precipitate. What that means is that if you have water molecules up here, and you put in a little bit of solid magnesium hydroxide, okay? So in other words, instead of ending up with magnesium hydroxide, if you started with magnesium hydroxide down in the bottom of the beaker, okay, and you let it dissolve. So what's going to happen is that some of this is going to ionize. You're going to produce some magnesium ions, and you're going to produce some hydroxide ions. So it's kind of, the analogy is similar to what's going to happen with a weak acid. If you have a weak acid, okay, if you have a weak acid, then that acid is going to turn into some hydronium ions and some anions. And your Ka is your hydronium ion concentration divided by your anion concentration divided by Ha. Okay? So it's the same format. So when you're talking about this stuff going from a precipitate out into the solution, we're going to start with the magnesium hydroxide as a solid, and then we're going to roll it into the concentration of the magnesium ions and the concentration of the hydroxide ions. So we talk about making a precipitate, but the precipitate isn't the story. The story is what happens up there in the solution, okay? So don't focus on the precipitate. You have to focus on the concentration of the ions in the solution above that precipitate, okay? So the story isn't who hooked up. The story is who hasn't hooked up and what's the concentration of the people that haven't hooked up yet, okay? That's the story, okay?
So for
Now-
once, we're focusing on the single people.
Yes, we're focusing on because the other people have hooked up, we don't care about them. Okay, so on page, you don't have to look at this, but on page 1093 in the back of your book, there is a chart of Ksp values, okay? So it's right beside the ones where you have Ka and Kb, okay? It's that exact same page, so what you have is Ksp. So if you look at magnesium hydroxide, okay, and this is going to be important in terms of how this is written. So this is solid magnesium hydroxide that's going to dissolve into some magnesium ions and two hydroxide ions. Okay, that's going to be important. I got magnesium ions turning into two hydroxide ions. Okay, yes.
Why does that do that? Because if you form precipitate, that means the bond between them is stronger than the water.
But it's the same thing that happens with an acid. This has a certain strength, but some of it will still ionize.
Okay.
Same thing is going to happen here. This is a pretty strong bond, but that doesn't mean that you won't have some magnesium ions and some hydroxide ions that are like, oh, we're
so
rebels.
when you form the precipitate, not all of the ions are forming precipitate.
Exactly.
Okay.
That's why I said the story is the solution that's up above, not the precipitate. Okay? Makes sense. All right. So here's what's important. These are ions. So we can talk about the molarity of the magnesium ions, and we can talk about the molarity of the hydroxide ions. What we can't talk about is the molarity of the MgOH2, because it's a solid, okay? You can't talk about like the concentration of a solid in water. You can talk about the concentration of ions in water, but you can't talk about the concentration of a solid in water. So when you look at Ksp, so this harkens back to a consistent theme. When you see the letter K, what does that indicate?
Equilibrium.
You're in equilibrium, okay? And that's the only time you ever use uppercase K. So if you look at the value of the Ksp for magnesium hydroxide, okay, that's 1.8 times 10 to the minus 11. So here's what this means. So your Ksp is going to be the concentration of my magnesium ions, okay, and it's always products of reactants, times the concentration of my hydroxide ions. Now, here's going to be something new. Maybe you saw this in Chem too. Because it's always products over reactants. Okay, in any equilibrium situation, it's always products over reactants. But if there's a 2 in front of the hydroxide, that means that that concentration gets squared. Okay? So this is going to become my magnesium ion concentration times my hydroxide ion concentration, but that's going to get squared. So what that means is that no matter what happens, if I multiply this magnesium ion concentration times that hydroxide ion concentration squared, this is what Mother Nature wants this thing to end up as. Okay? Just like if you have a Ka value for acetic acid, Mother Nature is going to do whatever Mother Nature has to do to get that Ka value. The same thing is going to happen here. No matter what, Mother Nature is going to get these concentrations to equal 1.8 times 10 to the negative 11. Okay? As long as it's in equilibrium. So what's going to happen is that I'm going to take this, right? That. And I'm going to add some water to it. And even though I've added quite a bit of water to it, okay, you'll notice that there's still some precipitate in there. So what's happening is that even though I have added more water to it, what's happened is that as I've added more and more water, Mother Nature wants these same concentrations to take place. So what's happening is that even though I've added water to it, Mother Nature is making some of these magnesium ions dissolve and some of these hydroxide ions dissolve to maintain that same equilibrium. So it's kind of like this. Let's say that for me to be in equilibrium, okay, which is pretty important, okay, I like my equilibrium, okay, I have to have like 17, or in this case 12 kids per unit of volume, okay? Now, that's when I'm in my wheelhouse. That's when I'm at equilibrium, okay? So if I make the volume bigger, I want to still be in equilibrium, okay? But the volume has gotten bigger, but I still want that same value. So what I'm going to do is I'm going to have to go out and I'm going to have to recruit some kids to come in and go, hey, I want to maintain an equilibrium. So me pulling kids from the hallway to come in here is like some of that precipitate dissolving because of the fact that it wants to maintain that equilibrium that's up above. Now, if I keep going, and I add a whole bunch of water, okay, what's going to happen is that I've still got that same precipitate, okay? I've still got that precipitate sitting there. So what that means is that even though I've added a tremendous amount of water, whatever these concentrations are up here are still going to be the same. Now, the same thing would happen if I reversed this. If I let that stuff evaporate and I let that water evaporate off, then I'm still going to maintain the exact same concentration of the ions to be in equilibrium. But then you reverse the process. So then it'd be like the room is getting smaller. I only want my 12 kids, so it's like, okay, you all are going to have to leave now. So if I let that sit out overnight and that water evaporates, I'm still going to maintain that same concentration of ions in the solution that's up above, okay? So that it's still in equilibrium. So as long as you ever see a precipitate, that means that the solution up above is in equilibrium. It's holding all of the ions that it can, and anything excess is formed as a precipitate. Okay? Cool with this. Right? So the story isn't the precipitate. The story is the solution that's up above. Now, a lot of times when you're dealing with Ksp and Qsp, Ksp means that you're at equilibrium. Qsp is like a snapshot to tell you what the concentration is at the moment that you mix them together. So this is important, okay? So when you're talking about QSP, QSP mathematically is the exact same way that you calculate KSP. It's still your magnesium ion concentration times your hydroxide ion concentration squared. What the QSP tells you is whether or not, after you mix solutions together, whether or not you're going to get a precipitate. Okay? That's the whole key. It's going to tell you whether you're going to get a precipitate. So what you'll see, and this will make sense, if your QSP is bigger than your KSP, like by a lot, by about a factor of 1,000, you'll get a precipitate. If your QSP is equal to your KSP, that just means that you're at equilibrium. If your QSP is less than your KSP, you don't get a precipitate because the solution isn't saturated and it's not holding the ions that it can. So you're going to have three situations. QSP is bigger, you're going to get a precipitate. QSP is equal to your KSP, it's just at equilibrium. QSP is less than your KSP, you're not going to get a precipitate. Okay? So, now, here's the most important part of this story. Okay, listen to me. Here's the most important part of this story. Okay? Is that your QSP is based upon the concentration of these ions after they are mixed. Okay? It's the most important part of the story. It's the concentration of the ions after they are mixed. Not as they are in the beakers, okay, or in the bottles, but it's after they are mixed. So we're going to run through two scenarios here. So, situation number one, I had 2 milliliters of magnesium nitrate. That is 1 molar. And then I had 2 milliliters of my sodium hydroxide, which was also 1 molar. Now, you can work in millimoles, you can work in moles. Personally, I'd work in millimoles so you don't have to divide by 1,000 and all of this stuff. So how many millimoles of magnesium nitrate do I have? 2, right? So I got 2 millimoles of magnesium nitrate. And I've got 2 millimoles of sodium hydroxide, right? Now, here's the deal. What I'm going to focus on is the concentration of my magnesium ions and the concentration of my hydroxide ions after they have been mixed together. So after I mix these two together, what's the total volume that I have? 4. So I need my concentration after they are mixed. So I'm going to take this, I'm going to divide this by 4 milliliters. I'm going to divide this by 4 milliliters. Milliliters cancel out. I get a half a molar solution of magnesium nitrate. And I got a half a molar solution of my sodium hydroxide. Now, hopefully that makes sense why that molarity dropped by half. Because I doubled the volume, okay, but I had the same number of ions. So if I double the volume with the same number of ions, the concentration becomes half. Just like if I've got 12 kids up here in this little area of the room, okay, that's my concentration. Now, but if I keep you 12, but I double the volume of the room, the concentration of my kids is going to go down by half. So if the volumes are equal, to get the new molarity, you just divide by 2. Okay? That's all you have to do. Just take your new molarity and divide it by 2. That's all you have to do. Okay? No worries. Now, so if I'm going to calculate my QSP, so my QSP is going to be my magnesium ion concentration times my hydroxide ion concentration squared. So in this situation, I'm going to take 0.5, and then I'm going to multiply that by 0.5 squared. So somebody take 0.5 squared times 0.5, or 0.5 cubed would be easier.
0.125.
0.125? Okay. Now, QSP and KSP have no units, okay? And here's why they don't have any units, because this would get really janky, because you'd have molarity times molarity squared, and then you got like molarity cubed. But sometimes QSP, like if it was just like silver chloride, it would just be AgCl, which would just be like molarity times molarity. So this is why QSP and KSP don't have any units, because there isn't like a standard way of doing it, because of the fact that they have all these different ways you can calculate in terms of molarity based upon your coefficients. Okay? So here's the story. So when I mix these together, okay, I have a QSP of 0.125. Now my KSP for magnesium hydroxide is 1.8 times 10 to the minus 11. So what that means is that when I mix those together, Mother Nature at this point flips out, okay? Mother Nature absolutely flips out. It would be like me walking in and going, hey, my normal capacity for you all moving around is 12, okay? I walk in and there's like 40 people in my room, okay? I can't handle it, okay? I flip out. It's like, okay, I can keep 12 of you, but the other 38 or 28 of you are going to have to sit down. Okay, go to the back of the room. You're going to be the precipitant. I can only teach my 12. Okay, the rest of you are out. Okay, you're gone. Can't handle it. Now, at that point, I become in equilibrium. Now, at this point, Jason goes, you know, Mr. Burkamp, I think I'm going to go walk up and stretch my legs. So he's going to go to the back of the room and he's going to hang out with the precipitate people. Okay. But if Jason goes and hangs out with the precipitate people, I want to maintain my equilibrium, so what's going to happen?
You're going to take one of the precipitate people.
Yeah, one of the precipitate people is going to come up here. So when you look at this, this isn't like a static situation. Okay? You're always going to have this exchange between the precipitate and the solution. But Mother Nature is going to maintain this. So basically what happened is because this value was so much bigger than what Mother Nature wanted to be in equilibrium, Mother Nature goes, oh, time out, okay? I can keep this concentration up here so that I maintain my equilibrium, but the rest of you I can't handle, you all need to sit down. And Mother Nature then forms that precipitate. So Mother Nature still wants this concentration. That's what she's after. And if there's too much, Mother Nature goes, sorry boys and girls, time for time out, you're going to have to sit down. So she's going to force them back as a precipitate, and that's what you're going to see. Now, let's say that I had done this. Let's say, and these are pretty concentrated values, like 0.5 and 0.5, right? So if I wanted to figure out what's the concentration when it's at equilibrium, so oddly enough, you can use a Rice chart, okay? And we could actually figure out what those concentrations are at equilibrium. So you can do the exact same thing.